Welcome to the 23rd lecture. So, we have been discussing about the Kepler's equation using graphical method. So, we will continue with that. So, as we have looked into this figure, so we derived we have these 6 equations 1, 2, 3, 4, 5 and 6. Using this we have to work out what we are looking for, this delta FAP, and once we know that, we will be able to work out the time taken from point A to point P. So, this there we have already done this part. This part we have to calculate delta NAP, and for calculating delta NAP we require delta NAM, okay. And NAM is given here. NAM is given here by this part, and out of these two are given here. So, we have to combine all these results. So, on the next page, first I write delta NAM. So, the area delta NAM, this equal to delta OAM, delta OAM minus delta ONM. And this is from 4. From 5 and 6. So, we can write here delta NAM, OM is given here, A square E divided by 2, A square E divided by 2, and this is ONM is 1 by 2 A square sin E cos E, 1 by 2 A square sin E cos E. So, this is our equation number 7. Now, once we have got this ONM and OAM, basically we are getting here NAM. So, now NAM is here in this place, okay. And from there we can get this delta NAP. So, from 3, therefore, from 3, therefore, from 3 we get here delta NAP, delta NAP equal to B by A times delta NAM, delta B by A times A square E by 2 minus A square by 2 sin E cos E, and this gets reduced to A can be taken outside, A B by 2 E minus sin E cos E. This is our equation number 8. Now, from 3 then we go to this, we write as here equation, this is 3, 2 already we have used. So, this equation we write as 1A. From equation 1A delta FAP delta FAP, this equal to delta NAP minus delta NFP, delta NFP. So, using delta NAP from NAP we have derived here in 8 from 8 and delta NFP from NFP we have derived here from 2. From 2 we get delta FAP, this equal to delta NAP. So, delta NAP we have AB by 2 E minus sin E cos E, AB by 2 E minus sin E cos E, and from there we have to subtract the equation 2, which is AB by 2, where AB divided by 2 E minus cos E, E minus cos E times sin E. And then we expand E sin E times cos E minus E sin E plus sin E times cos E. Okay. So, what we can observe that this term and this term they cancel out. So, this leaves us with delta FAP equal to AB times E minus E sin E. Okay, this is what we have got there. Now, we apply the formula delta A divided by A dot equal to T minus T, or where T equal to T p, position at the perigee, time at the perigee. So, here in this case delta A is nothing but your area F A P, area F A P, F A P. I hope now I can draw the line. This is not visible. This is from here to here, then this place to this place, and this. So, this is the area, the hashed area we are looking for, F A P. So, F A P divided by A dot So, this gets reduced to then a b divided by 2 e minus e sin e, and a dot is nothing but your h by 2. Therefore, t minus t, this gets reduced to a b divided by h e minus e sin, and we take it on the left hand side some of the terms, or we can first work out here itself and then take it on the left hand side. So, what we want to do, we want to write in terms of n, which is mu by a q under root mean angular rate, as we have derived earlier also angular rate. So, we do that here. A times b is nothing but a times a 1 minus e a square under root, and h is mu times L under root. So, h is mu times L under root, and this gives us mu times a times 1 minus e a square for an ellipse. Okay. And therefore, if we insert it here 1 minus e a square under root, this becomes a cube a to a square, 1 minus a square, this cancels out, mu to the power 1 by 2 times e minus e sin, and this implies, if we bring it on the left hand side, 3 by 2 and as we have already written here, this quantity is nothing but n. So, we write this part as n t minus t, and this quantity we write as the mean anomaly, which is just a mathematical quantity, no physical representation, unlike eccentric anomaly and true anomaly. So, this is your Kepler's equation using graphical method. So, this has been a very small thing, but doing and assembling from one page to another page, it takes time, but it is not a very long one. Once you know that, just you have to scale the area and scale the distance. These are the two basic concepts used in this, and the rest other is simple geometry. So, rest others are simple geometry which we have used here. Now, thereafter the question arises, how do we solve this? So, what we have got here, m equal to e minus e sin e. If we rearrange and write it, and then let us write y equal to e sin e and also y equal to e minus m, and plot both of them here e and y on this axis. So, this is e sin e. So, it will pass through the center and it will look like a sine curve. Okay. While y equal to e minus m, while e equal to 0, y equal to minus m. So, somewhere it cuts the y axis here, okay, and thereafter it has a positive slope of 1. So, it goes like this. So, wherever they intersect, So, this you can take as the starting point, which we will write as E 0. So, this is your E 0 and initial guess, and then there are various methods for estimating the value of E, because this equation, solving it, it is not straightforward, and therefore, we have to do it by iterative method. So, any iterative method So, as we have discussed earlier, that there are two problems related to what we term this as Kepler's problem. So, given R 0, V 0 at t 0, find R V and t. So, one way I have already stated this integrate means the numerical method can be used. The other way I have also stated R 0, V 0, T 0, this is converted first into A, E, I, capital omega, small omega and theta, the true anomaly, which I will write here as T 0, theta 0, and then propagate theta 0 to theta. So, at time t. So, how to propagate till time t? So, for that what we need? M equal to n t minus t. So, if you know the orbit, A is known to you and mu is known. Okay. So, therefore, this quantity is known to us. Therefore, to propagate theta 0 to theta, what we need to do? Find out m. Find m using this expression. Once you have got m, then m can be solved for E minus E sin E. So, using m, then you can solve for capital E, because E is small e is already known. So, from here solve for E. Once you solve for E, so now here E once known this can be used to solve for theta using the equations or the equation derived earlier, which I will again write due course of time, equation derived earlier. That means theta is a function of E, and therefore, once you have got this E, you can also get theta. So, this way you have solved for theta. So, what we have got here, the initial guess as E 0. So, this we can take as a starting point and solve this equation. M equal to E minus E sin E, this is our Kepler's equation. So, one very primitive way of doing this is write E equal to m plus E sin E, and then start with E 0. So, E 1 becomes, because m is known, this quantity is known, this we do not have to change, and this quantity is also known, this is also not going to change. So, we will start with sin E 0, we get E 1, thereafter whatever the E 1 we get, we use here in this, and so on. Okay. So, iterate till converges to desired accuracy. So, this is a primitive way of doing it. Another way of doing it can be using the Newton's method. So, there we need to write it phi E equal to m minus E plus E sin E. So, here what is happening that if m, the left hand side and the right hand side both are equal, okay, so this difference will be 0. Okay. If they are not equal, so this difference will not be 0. So, therefore, this is acting as an error function, and we want to minimize it. So, using the Newton's method, then we can work it out, okay. And this is pretty straightforward. Phi prime E, we write this as minus 1 plus E cos E okay. And thereafter the basic equation for the Newtons we use and work out this problem. So, I am just going to write it here. So, delta E 0, this will be equal to minus phi E 0 divided by phi prime E 0. This is the correction that we get. So, we can give it to E 0 this correction. So, E 1 equal to E 0 plus delta E 0 or delta E itself we can write here delta E. So, this is the desired correction. And how do we get it? This phi e plus delta e, this we can write as E 0 plus delta e, phi E 0 plus phi prime E 0 times delta e. And if this is minimized, if this quantity is minimized, means going from phi E 0 to phi E 0 plus delta e. So, if this is exactly the minimum, so the left hand side must be 0. So, from here then we can write delta E equal to minus phi E 0 divided by phi prime E 0. Once we have got this, so you just iterate this part. So, here we have phi this is E 1 equal to E 0 plus delta E, where E 0 already we have worked out using this method or using the graphical method, and then similarly E 2 will be E 1 plus. Okay, if we tag this as delta E 0, so it will be easy for us to do. Then this will be delta E 1. So, next step you calculate this delta E. So, this goes here in this place. Okay. Similarly, E 3 will be E 2 plus delta E 2, and this way we will be able to update it. Any other method you wish, you can apply Leavenworth marker or whatever is available. There are many methods of optimization. So, what we have to optimize? We have to minimize this phi, minimize it. Okay, so, we complete this lecture here, and we will continue with this lecture later on. Thank you very much.